Welcome to Chapter 3. In this chapter we'll use the practical skills from Chapter 1 and the concepts from Chapter 2 to dig deeper into logistic regression. Let's begin with logistic regression and regularization. The prerequisite course, Supervised Learning with Scikit-learn, mentions that regularization combats overfitting by making the model coefficients smaller. The figure shows the learned coefficients of a logistic regression model with default regularization. In Scikit-learn, the hyperparameter C is the inverse of the regularization strength. In other words, larger C means less regularization and smaller c means more regularization. Let's test this out. The orange curve shows what happens if we use a smaller value of C, which means more regularization for our logistic regression model. As expected, regularization makes the coefficients smaller. Let's see how regularization influences training and test accuracy. With the movie review dataset already loaded and split into train and test sets, we instantiate two logistic regression models, one with weak regularization and one with strong regularization. We then fit both models. Next, we compute training accuracy. The model with weak regularization gets a higher training accuracy. Now that we've studied loss functions, we can see why regularization makes the training accuracy go down. Regularization is an extra term that we add to the original loss function, which penalizes large values of the coefficients. Intuitively, without regularization, we are maximizing the training accuracy, so we do well on that metric. When we add regularization, we're modifying the loss function to penalize large coefficients, which distracts from the goal of optimizing accuracy. The larger the regularization penalty, or the smaller we set C, the more we deviate from our goal of maximizing training accuracy. Hence, training accuracy goes down. Let's look at the test accuracy this time. As we can see, regularization improved it. We discussed why regularization reduces training accuracy, but why does it improve test accuracy? Imagine you did not have access to a particular feature. That's like setting the corresponding coefficient to 0. Regularizing, and thus making your coefficient smaller, is like a compromise between not using the feature at all, setting the coefficient to 0, and fully using it, the UN regularized coefficient value. If using a feature too heavily was causing overfitting, then regularization causes you to fit less and thus overfit less. For linear regression we use the terms ridge and lasso for two different types of regularization. The general names for these concepts, outside linear regression, are L1 regularization and L2 regularization. Everything you learned about ridge, or L2, and lasso, or L1, in the past applies to logistic regression as well. For example, both help reduce overfitting, and L1 also performs feature selection. As an example, let's train two logistic regression models, with L1 and L2 regularization, on the breast cancer dataset after scaling features, which is usually good practice, especially when using regularization. We can plot the coefficients for both models, adding a grid so that we can see where 0 is. Note the solver argument used when creating the model with L1 regularization. This argument controls the optimization method used to find the coefficients. We need to set this here because the default solver is not compatible with L1 regularization. Here are the plots. As you can see, L1 regularization set many of the coefficients to 0, thus ignoring those features. In other words, it performed feature selection for us. On the other hand, L2 regularization just shrinks the coefficients to be smaller. This is analogous to what happens with lasso and ridge regression. So far we've been using logistic regression to make hard predictions, meaning we predict either one class or the other. In this video we'll discuss how to interpret the raw model output of the classifier as a probability. We've seen this type of decision boundary several times in the course. The fill color shows what class we would predict for every point in the space. In Chapter 1 we saw that the scikit-learn logistic regression object can output probabilities with the predict_proba function. Let's make the same type of figure but this time showing the probabilities. In this figure, the new interpretation of the colors is the predicted probability of the red class. The black line is the old decision boundary, which we can refer to if we need to make definite, or hard, decisions. We can see that this line is where the probabilities cross 0.5. In other words, if we're more than 50% sure it's red, we predict red, and if we're less than 50% sure it's red, we predict blue. We can also see that we get more and more confident as we move away from the decision boundary, which sounds reasonable. In this figure, regularization is effectively disabled because C is very large. The figure on the right shows what happens when we turn on regularization. First, we see that the coefficients are smaller, as expected. The effect of regularization is that the probabilities are closer to 0.5. We don't get to the very dark red or very dark blue on the right-hand figure. In other words, smaller coefficients mean less confident predictions. This fits with our story. Regularization is supposed to combat overfitting, and there's a connection between overconfidence and overfitting. By the way, These figures also answer a question you may have had from the previous chapter. With two features, we had two coefficients even though you only really need one number to represent the slope of a line. We now have a reason for this. The ratio of the coefficients gives us the slope of the line, and the magnitude of the coefficients gives us our confidence level. Finally, as you can see, regularization not only affects the confidence, but also the orientation of the boundary. So how are these probabilities computed? Like the definite class predictions, they come from the raw model output. The raw model output can be any number, but probabilities are numbers between 0 and 1. So we need a way to squash the raw model output to be between 0 and 1. The sigmoid function takes care of that for us. Here's what it looks like. Take a look at the curve. When the raw model output is 0, the probability is 0.5. This means we're right on the boundary. When the raw model output is positive, we would have predicted the positive class, and indeed the probability of the positive class approaches 1. When the raw model output is negative, we would have predicted the negative class, and indeed the probability of the positive class approaches 0, which is another way of saying that we're very confident it's the negative class. Since the raw model output grows as we move away from the boundary, we're more confident in our predictions far away from the boundary. Multi-class classification means having more than two classes. While we've used scikit-learn to perform multi-class classification, all of our conceptual discussions have been in the binary, or two-class, case. In this video, we'll discuss how multi-class classification works for linear classifiers. We'll cover two popular approaches to multi-class classification. The first is to train a series of binary classifiers for each class. For example, I've loaded the wine dataset and instantiated 3 logistic regression classifiers. I'll now fit these classifiers on 3 different datasets. The code y equals 0 returns an array the same size as y that's true when y is 0 and false otherwise, so the classifier learns to predict these true/false values. In other words, it's a binary classifier learning to discriminate between class 0 or not 0. The next one learns y equals 1 versus not 1, etc. This is called the 1 versus rest strategy. In order to make predictions using 1 versus rest, we take the class whose classifier gives the largest raw model output, or decision_function, in scikit-learn terminology. In this case, the largest raw model output comes from classifier 0. This means it's more confident that the class is 0 than any of the other classes, so we predict class 0. We can just let scikit-learn do the work by fitting a logistic regression model on the original multi-class dataset, setting the multi-class parameter to over. We get the same prediction, of 0, as expected. Another way to achieve multi-class classification with logistic regression is to modify the loss function so that it directly tries to optimize accuracy on the multi-class problem. You may encounter various words related to this, like multinomial logistic regression, softmax, or cross-entropy loss. The slide shows a comparison of the two approaches. In one case you fit separately for each class, whereas in the other you just do it once. The same goes for prediction. An appealing property of the binary approach is that you can reuse your binary classifier implementation rather than needing a new one. On the other hand, you might sometimes get better accuracy with the multinomial classifier since its loss is more directly aligned with accuracy. In the field of neural networks, the multinomial approach is standard. Finally, while both approaches can work for SVMs, 1 versus rest and related strategies tend to be more popular. By the way, both of these methods can output probabilities just like a binary classifier. We've talked a lot about the coefficients, so it's natural to ask, what do the coefficients look like for multi-class classification? Continuing with the wine dataset, let's fit a 1 versus rest model and look at the coefficients. In the binary case we had 1 coefficient per feature and 1 intercept. For 3 classes we now have 3 entire binary classifiers, so we end up with 1 coefficient per feature per class, and 1 intercept per class. Hence, the coefficients of this model are stored in a 3x13 array. We can instantiate the multinomial version by setting the multi_class argument to multinomial, which is also the default for non-binary classification. As we can see, the multinomial classifier has the same number of coefficients and intercepts as 1 versus rest. Although these two approaches work differently, they learn the same number of parameters and, roughly speaking, the parameters have the same interpretations. Thanks for watching. In the next video of the playlist, you will learn all about the details of support vector machines. You'll learn about tuning hyperparameters for these models and using kernels to fit nonlinear decision boundaries. Please feel free to ask any questions in the comments section. Like and subscribe to stay updated about our upcoming videos about artificial intelligence. See you in the next video.